All right. Good morning. Welcome in, everybody. Looks like everything's working properly. Okay, here we go. So welcome on in. Talking about statistics some more. So a couple of things here. One, if you have not taken the survey, so let me remind you how this is done. I made an announcement about it. I think, wasn't there an announcement? Yep, so there's a survey link up here in the announcements. Also, if you go down to the end of chapter 2, there's the link for take the survey. Okay, we have nowhere near the number of survey responses that we need. All right, this is the worst turnout I've seen from the classes where we've done this in the like 8 or 9 times where I've done this with classes. This is the worst. So in close to 40 people in the class, 16 people have taken the survey. So that's one since Monday. We cannot do the survey. You cannot do your projects properly with that few people. So we really need people that are in the class to go take the survey. If you need to, take the survey now. Right, and I realize I'm live. I'm probably talking to the people who have already taken the survey. If you're watching this at a later date, just go take the survey right when I'm saying this. It'll take you less than 10 minutes, and we need this in order to move the class forward. Okay, the original target date was yesterday, but 16 out of almost 40 just isn't going to cut it. So at this point, we're delaying people from being able to work on their stuff. So please. Like, that's number one priority right now. If you're in this class, go take the survey. Click this link right here under where it says take the survey in the modules. Click it and take it. Like, we really need it taken. Usually at this point, I'm pushing to get a few more people to take it, but at that point we have most of the class. Here we don't even have half the people having taken it. And now your ability of time, the time that you'll have to work on the survey is now shrink. You still have plenty of time, months, but you're holding up the class from being able to work on their stuff. So please go in, take the survey, and then we can try to move forward with this. Otherwise, at some point, I'm gonna have to release it anyways, and all your data is just gonna look terrible, right? You're gonna have it's gonna be much more difficult for you to try to do anything meaningful and useful with the data that you are collecting. So please get that done. Okay. Right. Okay. So with that said, basically take the survey. Okay. If you haven't done it yet, go take it. Where are we? And if there's some kind of issue or you're having a technical issue or something, get a hold of me. I'll help you figure it out. But we need people to go in there, click the link, and take the survey. Okay. All right. With that said, moving ahead, we are talking today about variation. So last time we talked about measures of center. That gives us an idea of where the data is located by somehow trying to pin down what we might think of as the center. But we saw that there's not just one way of thinking about the center of a set of data. You've got the mean, you've got the median, there's the mode. There's these different measurements that we use, although we usually stick to the mean and the median. But even then, we have two major ways of measuring the center that are very different from each other. And you always kind of have to figure out which one you should be using. All right, so that was one measure. That was one way of measuring a set that we looked at last time, the center of it. Today, we are looking at variation. So that is, how varied is the data? How spread out is it? This is very important. It's very important that we get this idea. But the very first thing you want to do whenever you have data is you take a look at the measures of center. You're going to look at the mean and the median, and then you're going to look at the variation, which is usually going to be the standard deviation. Those three things, that's step one when you're approaching data. That's the very first thing you do. You calculate those things, assuming it's appropriate, assuming that it's, the right type of data, right? That you're looking at like numerical data, quantitative data, right? Obviously, but if you're going to analyze quantitative data, that's the first thing you do: mean, median, standard deviation. So we're going to talk about the standard deviation today. So we have measures of variation, and just like with the measures of center, there are various measures of variation. There's different ways to talk about that. Although this one is a little more clear-cut. when you talk about measures of variation, you're almost always going to use the standard deviation. You will almost always mention that. In fact, I can't think of a situation where you wouldn't, right? In stats, you can never say anything for sure and just say you'll never do this. But I would have a really hard time thinking of a scenario where it would make sense to not consider the standard deviation of a set. You at least want to look at it, okay? And variation is really important, right, in a lot of different ways. In fact, the more you read about this kind of stuff, the more you realize, oh, it never occurred to me that variation was important for these kinds of reasons, right? So, they have these little asides in this book, and one is units, right? Units is a topic that a lot of students like to throw to the side, especially in a math class. They want to just do everything without using units, and a lot of times this leads to difficulties because a lot of times the units are the thing that guide you through the problem so that you know what step to do next by watching your units. Students like to throw them aside a lot of times. But this is units in the context of variation, right? So it used to be, back in the day, like hundreds and hundreds of years ago, there was variation in measurements, right? If you think about it, like you want to mark off a plot of land because you're going to buy a plot of land. Well, you want to know exactly where that boundary is because you don't want your your neighbor thinking that they own 3 feet into your land and you think you own 3 feet into their land. You want to know exactly where that is. So measurements are really important, right? If time is not kept properly, then that means everyone's going to be on different time. How are you supposed to schedule meetings and stuff like that? It just leads to a lot of inefficiency and a lot of problems. So, one thing that they've done over time is they've worked very, very hard to come up with ways of measuring time and distances which have as little variation as possible, right? Imagine, hundreds of years ago, 2 clockmakers using slightly different stuff. One clock runs slightly faster than the other clock. Well, whose is right? Whose is the correct clock, right? What's the real time? So it leads to all sorts of difficulties. So one thing that's been done is they've turned to science mainly to measure the second, right? What is the most accurate way we can come up with seconds? And over the last few hundred years, there have been different ways of doing this. Even looking at the motion of the Earth, like there's a lot of things that we as humans look at and we kind of just take for granted that they work the same way every time. But even the Earth, the movements of the Earth change over time, right? For different reasons. Different things affect the motion of the Earth. Sometimes even like a volcano going off somewhere or a big earthquake can slightly affect the motion of the Earth and throw it off just a tiny, tiny bit. So even those kinds of things were not accurate enough. So what scientists do now is they look at the basically the radiation period of is it a cesium atom? Yeah, a little cesium atom. So basically, how fast is that thing radiating? And they have a machine that can count those. So there's a certain number of after a certain number of radiations, that's 1 second, right? So this is done with these. You've heard about these atomic clocks. I think one's in Colorado. It's like underground, so it's super, super safe, and no one's going to mess with it. And then the whole world kind of bases a second on that clock that's buried in Colorado. And at that point, the second has very, very little variation, right? I think this thing says it's plus or minus 1 second in 10 million years. Well, at that point, we're all showing up to our meetings at the same time, So it's actually quite important. Our society runs better when we have a second that doesn't have a lot of variation, right? When we don't have 2 different clockmakers making 2 different clocks, and so we don't know, well, is that guy's 1 second or is that guy's clock 1 second? We don't know, right? In this way, we've shortened that variation down to very, very small. And then we can all understand time better. We can keep track of time. We can reset our clocks. We can do everything we need to do so that we have the right time. So that's an example of real world where variation is important, understanding that variation. This is the same thing if you're doing like quality control in a company, you're producing parts. Well, we're used to when you buy something, most of the time the part you buy looks right. Okay, but everything coming off the assembly line is oftentimes doesn't look right. Right? A lot of times they have someone sitting there looking, go, oh, this bolt is deformed. Okay, they throw it in the bucket to be reforged, and you're pulling out the bad ones. So quality control in a company is important. You want to know, like, of these parts that we make, how many are coming off right and what can we do differently? That's variation, right? The parts are varying a little bit, and you want to try to minimize that as much as you can, because any parts that you have to redo or throw away, that's money being wasted at your company. So you want to reduce that variation as much as you can. Now, so it's important that we understand variation and what to do with it. Let's see, where was I? Right. Okay, so measures of variation. Let's take, for example, let's look at some test scores. Okay, so I give tests to two identical classes. One class, every single person in the class gets an 80. Okay. Is that 10? Yeah, okay. Oops. Okay, so two classes, right? I've got class 1. We'll just call this class 1. And we'll call this one class 2. So I give two different tests, right? And I've got the one class, everyone scored 80 exactly. The other class, half the class scored 60 and half the class scored 100. Okay, well, that's very different test results. Like if you're, when you're a teacher, you give a test and then afterwards you look at the test results and you kind of go, okay, so what is this telling me about the class? How much do they understand? Where are they at? These two classes have a very different understanding of statistics, or whatever the class is that this hypothetical test is taking place in. We'll just say statistics. Here, everyone understands the material decently, right? Over here, half the class understands it really poorly. Half the class understands it really, really well. Okay, well, that's kind of weird. That's a different behavior. Well, look what happens if I go and I come up with the summary stats for class 1. Right, so that's class 1. And then we come up with the summary stats for class 2. And we look at our measures of center. So the measures of center, we had the mean. Oh, look, they match, 80. Look over here at the median. Oh, they match, 80. So when it comes to center, like these are obviously very different sets of data. And yet, when we looked at the measures of center, they can't tell any difference. Our measures of center might be useful to talk about, but they're not useful in any way about telling us any differences between class 1 and class 2. Even though the behavior of these classes is quite different, the measure of centers don't tell us anything about that, right? They're not helpful to us in that way, because the center of these two data sets is in the same place, but it's not capturing that there are fundamentally different characteristics here. So what are we going to do in order to be able to describe the fact that there is some very clear differences between these two sets, but I don't have tools yet to know how to describe those differences? What am I going to do that shows me the differences between these? And the answer is the standard deviation. If we look here, which we'll sort of talk about in a few minutes, but we're really getting at the variation. How much variation is there occurring? How much do my data points vary between each other in the set? Well, up here, this STD dev, that's standard deviation. That's your go-to measure for variation. You sometimes might use the variance, but not as much. Standard deviation you're always going to look at. You might sometimes include the variance or one of these other ones, but standard deviation you go to. Notice that for class 1, our standard deviation is 0. That is, the variation between our data points is 0. There is no variation between the data points in class 1, right? Deviation means to change, to be different than each other. So it makes sense. What is the deviation of this set? Nothing. The points don't deviate from each other at all. They are all identical. Okay, then we come over here for class 2. Oh, my standard deviation is 20.519567. Oh, so we see there is a large deviation in the second class. There is a big difference between some of these data points, right? So that's what we need, is some kind of, that's what we're talking about here with variation. We're looking at how much do the data points vary from each other. And when we talk about that, the stuff we talked about last time, the measures of center, although they're very useful for some type of descriptions, they are not useful at all to us in this type of hypothetical scenario I came up with. So it's becoming clear that, oh, variation is something that we need to investigate each and every time we look at data. And that is true. That is exactly what we need to do. Okay, so let's go to the book here. Let's look at some actual definitions. Or let's look at another one first before we get into it. Here's another reason why it might be important. Imagine you're either the consumer, or imagine that you're the producer of some cookies. Okay, so they look at the number of chocolate chips. Well, apparently if you look at Chips Ahoy, the regular brand, there's this big variation in the number of chocolate chips that can occur in, what is this, per cookie? Dot plots of numbers of chocolate chips in cookies. That seems like a lot. 30 chocolate chips in the cookies. Anyways, see how the center of these two sets is roughly the same, right? So that would mean that on average, you would expect either one of these types of cookies to have about 24 chocolate chips in them. So that's that center again. But depending on the type of person you are, you might not want to eat these Chips Ahoy. You might go, man, that's really great when I get one of these cookies that has like 30 chocolate chips in it. But then you're really bummed out when you get one of these chips that has 18 in it, right? And you're like, I don't even like what would this be? Maybe 10%. I don't even like 10% of this bag because I hardly got any chips in it at all. Or maybe you're sharing. You and your friends all get a bag or whatever they call those containers that are kind of part bag, part box of Chips Ahoy, and you share them with your friends, and then like the 3 cookies you get are all down here. You get like no chocolate chips, and then your other friend, they get like all these up here where they get tons of chocolate chips. Like, you're gonna be a little sad, right? A little sad in your heart because you didn't get enough chocolate chips, right? Even though the mean is about the same for each of these. Whereas if you'd bought this other brand, I'm not familiar with this, but Triola chips, they're pretty consistent. Every cookie has either 23, 24, or 25 chocolate chips in it. And you're probably not going to notice that difference when you're eating it. When you're eating cookies, you might notice the difference between, I guess this is 19 chips and 31 chips. You're probably not going to eat one of those cookies and go, oh, man, I got one of the ones with 23 chips in it. I wish I'd eaten one of the one with 24 chips in it, right? So it's more consistent. So that's a measure of variation. We're seeing that the Chips Ahoy cookies vary a lot, and the Triola chips vary very little, right? So it just kind of matters which ones which do you like? What do you prefer as a consumer? Are you going to be so bummed out by these ones down here that it makes you want to throw the whole bag away? And then you just want this where everything's roughly the same every time? That's kind of what we get with like processed food, cookies and stuff like that for the most part now. Everything's supposed to be identical, right? Everything in there is identical to every other thing in there, and every bite you take is supposed to be identical to every bite. That's one of the things they kind of strive for with processed foods. It's all just like, like they're clones of each other. So this I bet this data wouldn't even hold up anymore. I would guess that Chips Ahoy is probably tightened things up so it's a little tighter. But you can see the difference in that if we took the mean here, we're going to get the same thing. But the variation is apparently telling us a different story. It's telling a different story about these things. Whereas Triola chips is very consistent, Chips Ahoy very inconsistent. Okay. So we have these different measures of variation, just like we had different measures of variation for, we had different measures of center for statistics. We have different measures of variation. The range is one. The range you might just mention, but it's not going to be the main tool that you use if you're going to be presenting things. You might throw the range in there. The range is actually really useful if you're going to make a graph and you kind of want to know, okay, how wide do I need to make this thing? I need to know how, like, where's all my data going to fall? So what you do is you take the maximum data value minus the minimum data value. That just tells you the distance between your highest and lowest value. Well, that's helpful if you're going to make a graph. And you go, well, I want the highest value over here. Like, if your data values only vary by 20 points, then you're not going to make a graph where the x-axis is 100 wide, right? Because all your data is going to be just crunched right in the middle. Well, what's the point of that, right? So a lot of times that's one of the big things you think about with the range is you think about the, like, if it's kind of for planning how you're going to do other stuff. Okay, here's the big one, the standard deviation of a sample. Now, the standard deviation of a set of sample values, denoted S, is a measure of how much data values deviate away from the mean. It is calculated by using the formulas below. Good news, you don't have to know these formulas. You should look at them and just try to make sense of them, because actually understanding these values gives you some pretty good understanding of what exactly is being calculated. But you're not going to have to sit down and calculate these. When I do this in class, when we have more time, I make students do one example standard deviation by hand with only a few number of points, like 6 or 7 points, maybe 8 points. Past that, it starts to get a little tedious because you have to do like calculations on each piece. But you know, for 5 or 10 minutes to figure that out, it really helps give an understanding of how that works. So I think there's one in here. Yeah, they do one by hand here, calculating standard deviation with formula 3-4. I would encourage you, just look this over, because the standard deviation is one of those things that when you see this formula, your brain is just like, I don't know, that looks really complicated. I'm just going to have StatCrunch do it for me, which is what we're going to do most of the time. But it's actually a formula that you can break down and understand pretty well, right? You can look at it and go, oh, I get what's going on here. And it makes sense, right? So anyways, yeah. So basically what you do, so I'll go over it because, again, just understanding the formula is actually really helpful. You take your mean, right? The mean is x bar, and you take each data point minus the mean. So what is that? When you take a data point minus the mean, it's telling you the distance between your data point and the mean for your data. So the first thing you have to do is calculate the mean. Then you go through for each data point, and you do that data point minus the mean, and then you get a number. Go to your next data point. That data point minus the mean, you get a number. Your third data point minus the mean, you get a number. And you're getting all these distances of how far your data points are away from the mean. Now you'd think, well, maybe I should add those up, which is very reasonable to think, because if we add up all those distances, then that should tell us how far our points are away, except there's a problem. If you do that for every data point, you take the data point minus the mean, and you get all these different values, and you add them up, you will get 0. So that doesn't work. It's a good idea, right? It's probably the first thing they did when they were trying to understand statistics was, oh, let me add up all the distances from the mean. Oh, look, I get 0 every single time. Okay. So what they do is they take the distances between the data point and the mean, and they square it, because that makes them all positive. They're not going to cancel anymore. So we take those distances, we square them. Remember, this just means add them up. And then we divide by n minus 1, which is the size of your sample minus 1. You might go, well, why aren't we dividing by n? There's a mathematical reason why we don't divide by n, but it's probably not worth us going into. So just keep in mind, we're summing up the squares of the distances between the data point and the mean. We add them all up, we divide by n minus 1, and we take the square root. And you might go, why are we taking the square root? Well, it doesn't exactly undo the squaring process earlier, but it kind of smashes it down. It reduces it. It minimizes this weird squaring that we do. In fact, if you don't take the square root, you end up with another thing called the variance, which comes up from time to time, but you probably won't use as much in your project as you will use the standard deviation. Okay, so it actually makes sense. Okay, we're taking the distances between the data point and the mean. We square them so that they don't cancel each other out. We add them all up, divide by n minus 1. and take the square root. It's actually a reasonable thing to do. Like, it's very followable, whereas some people look at this and they're just like, I don't know, my eyes are glazing over. But it's pretty reasonable to follow through with what that is. So I would encourage you when you're doing the homework, just try to follow this example too. There's only, 1, 2, 3, 4 values. So they walk you through finding the standard deviation. It's not very, they literally do it here for you. So you could just, calculate them all. You can see right here, look, these are the distances. Like, okay, so let's walk through it. But I would encourage you to take a few minutes to try to understand it when you do the homework. So we compute x bar. That's the mean of the data values. Okay, they do that right here, and they get 23.5. Then they go through and they do all the x minus x bars. They get all those distances. But look what you get. You get negative 1.5, negative 1.5, 2.5, and 0.5. Well, if I add those values up, what do I get? 0. Right? Just like I was talking about, those data values would end up being 0. That means if we did it that way, every standard deviation would always be 0. That's not a useful tool, right? So what you do is you square the standard deviations, or you square the deviations, sorry, and then you get these numbers. You add those up to get 11, divide by n minus 1, take the square root, you get 1.9149. Right? So that means that our standard deviation for these chocolate chips is about 1.9 chips for this data set. Not the big one we looked at a minute ago where we were looking at the dot plot. This has way too many. The one we were looking up here, way too many data points. You would get annoying to take the time to find the standard deviation for this one by hand. But if there's only 4 points down here, it's a lot easier to follow through. So it's actually quite understandable to understand that standard deviation and what makes sense of it. So don't think of it as some magic formula, right? You don't want to get to where StatCrunch is just a magic box for you. You push some buttons and some kind of magic occurs, and then you get a number back and you're like, I don't know who this number is or where it came from, but it's the one I'm looking for, and do it that way. Okay, just try to understand what's going on in there about what's happening. Okay, where are we? Right. Right, okay. Where am I? So there's this range rule of thumb. So remember we talked about, before about outliers. So technically we're not yet defining outliers, but we have these interesting data points, right? How do you know when a data point in your set sort of lies within the normal, like, I got to be careful using the word normal, right? Within a typical grouping of data points, and how do you know when one is far enough away from everything else that it should be investigated, that you should take a closer look at it? So we have this thing called the range rule of thumb, and it's just a rule of thumb is not an exact rule. It just means that it's kind of a guideline, right? So this is not something that's written in stone. It's just a guideline to tell you maybe when you should start paying a little bit of closer attention to points. Like whenever you have something that is obviously an outlier, you should always look at that, right? But how do I know when something is far enough away from the rest of the data points to merit a closer look? Well, that's what this range rule of thumb says, is once something is 2 standard deviations above the mean or 2 standard deviations below the mean, you should take a closer look at it. Okay, you should look at it and go, is there something that I can learn from looking at this data point? And oftentimes the answer will be yes, right? You can figure out what is different about this. Why is this one thing different than everyone else or everything else that's in your set? So this is an idea that we'll be building upon, is counting the number of standard deviations something is away from the mean. Once you're 2 standard deviations away, you kind of look at it and go, I wonder if this data point can tell me something. I wonder if there's something I can know about what's going on. Okay, so just keep that in mind, right? 2 standard deviations away is worthy of a closer look. And you might go, well, how do I know if something's 2 standard deviations away? We're going to get to that in the future. I don't remember if we're going to get to it today or if we'll get to it next time. But that's part of. I think it might be this section. That's part of what's coming up. Okay. Here's another example of variation, very important. So more stocks, less risk, right? So you might hear about people investing in stocks, and you hear this term diversify a lot. Well, whereas most people, when they get excited about stocks, they just want to take their money and throw it all into one stock and see how it does. And sometimes you do well for a while. Most of the time that ends up being a losing strategy because it's risky. At that point, you're essentially gambling, right? What most financial experts recommend is that you diversify. So that is that you don't just buy one stock, right? So sometimes people go, well, I don't really have enough money to buy a whole bunch of stocks. I just have enough money I can buy one stock. And so then you have what are called mutual funds, which a mutual fund is where they buy up a bunch of different type of stocks, and then you buy one of the mutual funds, and then what happens is your money is sort of spread out over different stocks. Now, what does this do? It limits your variation so that you're not going to have the big highs and big lows, right? So you might go, well, that's the whole point, right? Is don't I want to catch the big high? Yeah, but most people end up catching the big low, right? And then they get scared and then they sell. There's the whole idea you're supposed to buy low and sell high. People tend to do the opposite, actually. If you look at what people actually do, they hear about a stock, they're getting excited, they watch it rising, and they're like, man, I gotta jump on this bandwagon. They buy, and then the stock dips and they get scared and they sell. So you're supposed to buy low, sell high, but most people do the opposite. They buy high, get scared, and sell low. But what they say is that's generally a losing strategy. What you want to do is buy lots of stocks. And so that's why they recommend the winning strategy for most people, unless you're going to spend your day studying stocks, right? If you're someone who's going to sit in front of the TV, watch CNBC all day, read your financial papers, yeah, you can make money on stocks. But it kind of has to become your life. You're not really going to get rich on stocks by like spending 30 minutes a day looking at some stocks. I know people who have done well, but it's their hobby. It's what they spend time on all the time, and they're super knowledgeable on all the things that are going to happen, right? So for the average person, what you do is you invest in some type of an account, like a retirement account is what most people want. I want to make sure there's some money when I'm old and I can't work anymore. There better be some money there for me. So you put money in an account. Usually that should be distributed over a lot of stocks in a mutual fund or something like that, so there's less variation. Now, why is that important? Well, many of you were just little children at the time, but if you remember back to 2008, there was a massive crash in our economy, right? We have the way our economic system works. Every 3 to 5 years, you have what's called a recession, and you lose a bunch, and the recessions are getting worse in the last few decades because of the way we run the economy. The recessions are bigger and bigger, right? So we had a huge pullback in 2008. People lost a lot of money. Well, it turns out there was a lot of people who were just a few years away from retiring, and they had a lot of their retirement in just a handful of stocks. And you literally would just, like, everyone you knew who was close to retirement is like, my retirement account is worth half what it was yesterday, right? You would hear this all the time. And kind of those people set themselves up for failure because they set themselves up for those big drops, that big variation, that big loss. What you're supposed to do, so one of the accounts that I have for my retirement, it's called a target account, where it's actually managed by computers. There's very little human interaction, which also means you get less fees, but that's a whole rabbit hole to go down. But what happens is it has a target date for your retirement. So you say, I want to retire in this year. So what it does is every year you get closer, that holding, it changes what's in there. So basically it spreads out to more stocks, and it starts buying bonds instead of stocks and stuff like that. So people who were in if you were in 2008 and you were in that type of retirement account that I'm talking about, where it automatically diversifies every year, those people might have lost 10 to 15% of their retirement account, whereas their neighbor who is in the same situation wanting to retire a few years later lost half of their retirement account. I mean, imagine you've spent 40 years saving up money. You're 5 years from retiring, and the next day your account is half what it was. That's pretty heartbreaking, right? And unfortunately, people were doing unfortunate things because they were very sad about their stocks and stuff like that. So that's another way that sort of affects your life, where variation is important. When you're saving for retirement, you don't want a ton of variation, because you can end up losing 10, 15, 20 years of gains when we go through these big unfortunate drops that are built into our system. So another reason why variation is important. Okay, standard deviation for a population. Okay, this is important because you'll have problems like this in the homework. Okay, so there's a different formula for the standard deviation of a sample versus the standard deviation of a population. Now let's remember what that means. A population is when you know the information about everyone involved. Like everyone that you're trying to study is the population. We almost never have that, which is why most books sort of they don't put as much emphasis on this. You need to know it, but we don't usually study a whole population. We almost always study a sample. That is a smaller subgroup of the population that we're looking at, right? The survey that I need more of you to take, and that you need more of you to take, that would be considered a sample, right? It wouldn't be a great sample because we didn't randomize it, but technically that could be considered a sample for Ventura College students. Right? We didn't really do this in a rigorous way where we can like publish papers or anything like that based on our data, but you get the idea, right? This class is a sample of Ventura College students. So if we were going to use the standard deviation for our class, we would use that formula I looked at earlier. Remember where we had the n-1 in here? Whereas if we knew if we had data for every single Ventura College student and we wanted to look at the standard deviation of, say, age, we would use this formula if it was for the entire population. Okay, so look closely in StatCrunch. Pay attention, because there's going to be problems where they say, treat this data as a sample. And there's going to be times when they say treat this problem as a population, because you're going to be looking for two different standard deviations. So when you see, we use little s. Remember up here it said we use, in this definition, it said to use, so we use s, lowercase s right here. That's the standard deviation for a sample, right? Sample standard deviation. When you're trying to do the standard deviation for a whole population, then you're going to use, where are we? We use sigma, lowercase sigma right here. This symbol right here is called lowercase sigma, just sigma. The capital sigma is actually this one over here. So sigma gets used twice in this formula, but for different things. Capital sigma means add things up. Lowercase sigma means population standard deviation. In real life, you'll almost always be taking a sample standard deviation, but you will have homeworks that ask for this, so make sure you realize you're looking for a different thing. Okay, pay attention to that, because I know my full class, my 16-week class or 18-week class, some students got confused on the homework because they were still looking at the sample standard deviation and they were getting the wrong numbers when the problem said treat this as a population. So make sure you're grabbing the right thing when you do those homeworks, okay? Right. Okay, now we have this thing called the variance. And the variance gets used in certain situations. We probably won't use it a ton in this class. If you're going to go on and take more statistics in the future, variance will come up more often. It'll play a larger role. But in the beginning stages, standard deviation is almost always your go-to. Okay, but the variance is easy to calculate. It's the square of the standard deviation. Remember in our standard deviation formula, we take that square root. Remember the square root? If you don't take the square root at the end, you get the thing called the variance. This would be for the population. But basically, if you don't hit square root at the end of your calculation, you have calculated the variance. Then you hit square root, you now have the standard deviation. So it's actually pretty easy to get our hands on. So the variance of a set of values is a measure of variation equal to the square of the standard deviation. And you might go, well, why do we need that? There are certain instances where it's better, right? And we're not going to go too much into those so much. Yeah. So variation means just how much things are changing. Variance is actually a specific definable measurement in statistics. So if you see variance, you're looking for that. And it gives that in StatCrunch, right? When we did this, where are we here? See how it's giving you? You've got your standard deviation and you've got your variance in there, right? Oh, let me show you also. Let's say we're going to check the stats, summary stats columns. You've got your unadjusted standard deviation. That's that other one that you're going to occasionally have to look for. Okay, your unadjusted standard deviation. That's the population one. Okay, so that you see how to get that. You just, instead of clicking these, you know, I think if you hit shift, you can keep all the ones that you had previously, right? If I do shift, oh, it does all of them. But now when I compute it, oops, I need to do this. Let's do this one. Compute. It's now got your standard deviation that we had before, but it's also got this unadjusted, oops, that I do unadjusted variance. I accidentally grabbed the variance when I did that. So let's redo that. I thought I grabbed this one. There we go. Unadjusted standard deviation, class 2, compute. There we go. Unadjusted standard deviation showing up at 20. Okay, which is a little, notice that's different than our standard deviation. So when you're doing the problems on the homework, 20.519 is going to come out differently than just straight up 20, right? It's going to come out a little bit different. So make sure you know which one of those you're looking for, the standard deviation or the unadjusted standard deviation, and that is the difference between a sample and a population. So if you think you're doing it right and you're putting the deviation in there, try the other one, see if that works for your problem. That's probably going to fix it for you. Okay? All right, so variance comes up. One of the nice things, did I skip? I thought I had a paragraph in here that I must have skipped somewhere. Oh yeah, here we go. So important properties of the standard deviation. The standard deviation is a measure of how much data values deviate from the mean. So we're using the mean as like the landmark, and we're measuring how far everything is away from that. The value of the standard deviation is usually positive. It is 0 only when all the data values are the same number. So notice that, and it's never negative. So notice that when we did our problem here, when did we get 0 standard deviation? That's when every single data point was the same. If I changed even one of these to be an 81, here, let's make this one an 81. And then I go and look at summary stats, columns, class 1, compute. Notice that standard deviation is not 0 anymore, right? It's small, but there's a little bit of deviation between those points now. So the only time you get a standard deviation of 0 is when all of your points are identical. Okay. Otherwise, it's positive. You never get a negative standard deviation because you end up squaring all those differences, so they all become positive. So how would you get a negative? You can't. And the larger your standard deviation is, the more spread out your data is. Okay, so if you get a large standard deviation, that means your data is very spread out. If you get a very small standard deviation, that means that your data is very tight together. Remember the dot plot we saw at the beginning of the class? The Chips Ahoy would have a larger standard deviation than the, whatever the other one was called, where there was only like three different data values, like in the chocolate chips. The value of the standard deviation S can increase dramatically with the inclusion of one or more outliers. So if you throw one outlier in there, your standard deviation could really skyrocket. Okay, it can really go up a lot. So it's kind of like our mean. Remember how the mean was really affected by outliers, but the median was not? The standard deviation can change a lot based on an outlier. Okay. And here's one thing that comes in handy. The units of the standard deviation S are the same as the original units of the original data values. That's convenient because if you're talking about something that is, say, a number of chocolate chips, then it's nice that your deviation is expressed in chocolate chips, whereas the variance would be expressed in chocolate chips squared. And that gets confusing because you're like, what is a square of a chocolate chip? What does that mean? Like, what is that value representing? And it can just be a little disorienting, a little bit confusing to go, how do you square a chocolate chip, right? And then you have to sort of mathematically break down what that means. The sample standard deviation S is a biased estimator of the population standard deviation sigma, which means it's basically it's like what we talked about up here. It can be it can vary quite a bit, so you don't always know. Those outliers can throw you off quite a bit, so you have to be careful about that. Okay, I wanted to make sure I got those points in there. Yep, standard deviation for a population. So look out for that on the homework. Always ask yourself, are they asking about a sample or a population? And it's either obvious it should be obvious in the problem. Okay. The variance, you get different units. That's one of the problems, but it is an unbiased estimator, so it's a little more stable, right? Let's see. Then they go into other ways, like basically other versions of deviation that you can use. Notice how here they're not squaring them; they're taking the absolute value. That's another way that you can measure deviation. We're not going to get into that, right? It's called MAD, mean absolute deviation. It's another way of doing it. It almost seems more logical this way, but it turns out for some reasons that in statistics you actually use that less often than the standard deviation. So for certain reasons. And then there's some answers in here if you want to read deeper about like, well, why do we divide by n-1 instead of n? Like that's the two differences between the two standard deviation formulas. Feel free to read you can read up on that and figure it out. Let's see. Oh, this is kind of a graph that you'll see a lot, which is useful. Remember when we talked about a normal graph, capital N normal, not lowercase normal like we're saying, oh, it's just kind of a typical thing, like capital N normal, right, where you have a symmetric bell-shaped set of data. You can roughly count on these numbers. So what is this? What is our x-axis? Well, x bar is our mean, and S is standard deviation. So what that means is if you start at the mean and you go up one standard deviation, around 34% of your data will be in there. This will vary a little bit, but about 34% of your data is there. Also, if you go down one standard deviation, 34% of your data is there, which means approximately 68% of your data falls within one standard deviation of the mean. All right, go out a little farther. What about if we go 2 standard deviations out? Okay, well, that means that 95% of your data lies within 2 standard deviations. Okay, and within 3 standard deviations, you should have 99.7% of your data. Now, that's for a very large data set, like really, really big, and normal, right? Capital N normal. So most of the data sets that we deal with in this class on the homework and stuff like that, you're probably going to find 100% of your data is within 3 standard deviations. But this is for like really large, really well-behaved data sets. You get this kind of behavior, which means, if you do stats a lot, you have these numbers memorized because then you just kind of know, oh, yeah, I'm within 2 standard deviations, so that's going to be 95% of my data, and you sort of go from there. Okay? So you don't have to memorize that, but this is a picture you should understand what this means and then sort of think about how like, what are the implications of that, okay? You've got coefficient of variation, which I don't think will come up a ton. Right. And then, yep, so it looks like we're out of time there. So that's your variation lesson. Basically, standard deviation is the one you're going to want to go with most of the time. You might also look at the variance and stuff like that, but standard deviation is kind of your go-to. So number one thing, right, and probably I'm talking, at least live, I'm talking to the people who've already done it. Please go take the survey now. I was hoping to release the results today. I cannot do it with 16 people out of almost 40 people in the class having taken it. So please go take the survey. Just do it now. Do it before you do your homework. Do it before you do anything else in this class. Just take the survey, okay? It's you'll want to start working on your project. So especially since we have an upcoming. Where's this? What's the next one we have coming up? That one's passed. Take the survey. Yeah, so these are coming up. I'll assign these. I guess I haven't assigned them yet because I didn't know when I was going to be able to release the data. But you don't want these to start backing up, so you have to do them at a later date. You want to be able to start doing these live. So please get in there, take the survey so that I can release it. Can't do it with 16 data points. Otherwise, I will see you next week. Anyone who wants to hop into Zoom and talk to me about the class, ask me questions, get help taking the survey, whatever you need so that we can move you and the class forward successfully, please hop into Zoom and discuss things with me. Otherwise, keep up the good work. Stay current on the homework, all that kind of good stuff, and I will see you next week. All right, thanks, everybody.